Hey there, future chemists. Today, we're diving into the fascinating world of aldehydes. Aldehydes are a class of organic compounds found everywhere in nature. They give cinnamon its warm aroma and vanilla its sweet scent. Intrigued? Let's learn more. So, what exactly are aldehydes? They're molecules characterized by a carbonyl group, CEO, at the end of a carbon chain. Their general formula is RCHO, where R represents any alkyl or aryl group. Remember that CHO at the end? That's the aldehyde's signature. Think of formaldehyde, the stuff used to preserve specimens in jars. It's the simplest aldehyde with just a hydrogen atom as its R group, HCHO. Then we have acetaldehyde, CH3CHO, found in ripe fruits and, unfortunately, in hangovers too. From fragrances to flavors to even biological processes, aldehydes play a crucial role. Ready to uncover the secrets of making these versatile compounds? Let's get started. Let's zoom in on the heart of an aldehyde molecule, the carbonyl group, CEO. This group consists of a carbon atom double bonded to an oxygen atom. This double bond is the key to an aldehyde's reactivity. The carbon atom in the carbonyl group has a partially positive charge. The oxygen, being more electronegative, carries a partially negative charge. This difference in charge makes the carbonyl group polar. This polarity makes aldehydes great at reacting with other molecules. They can attract molecules with opposite charges, leading to the formation of new bonds. This reactivity is what makes aldehydes so versatile in various chemical reactions. Understanding the structure and the carbonyl group's properties is essential to grasping how aldehydes are synthesized. Now, let's explore the fascinating ways we can prepare these important compounds. One way to make aldehydes is by oxidizing a primary alcohol. Imagine you have a car and want to give it a little more oomph. You wouldn't swap out the whole engine, right? Similarly, in chemistry, oxidation is like fine-tuning a molecule by adding more oxygen or removing hydrogen. For this transformation, we use a special reagent called PCC, short for pyridinium chlorochromate. Think of PCC as a skilled mechanic who knows exactly how much oomph to add without going overboard. In this reaction, PCC selectively oxidizes the primary alcohol. This means it only adds one oxygen atom to the alcohol, turning it into an aldehyde. The controlled nature of PCC prevents the aldehyde from further oxidizing into a carboxylic acid. This method is like giving your car that extra boost without turning it into a whole new vehicle. Section 4. Dehydrogenation, a balancing act for aldehyde synthesis. Another cool way to create aldehydes is by dehydrogenation of alcohols. It's kind of like removing weight from a race car to make it go faster. By taking away hydrogen atoms, we can transform an alcohol into an aldehyde. We use a hot copper catalyst for this reaction, typically at a temperature around 300 degrees Celsius. The copper acts like a facilitator, helping the alcohol lose those hydrogen atoms. During dehydrogenation, two hydrogen atoms are removed from the alcohol molecule. One hydrogen comes from the OH group, and the other comes from the carbon atom attached to the OH group. This method is particularly useful in industrial settings for large-scale aldehyde production. Section 5. Ozonolysis, cleaving alkenes to form aldehydes. Now, let's talk about ozonolysis. Imagine splitting a log of wood in half. Ozonolysis is similar, but instead of wood, we're cleaving a double bond in an alkene molecule. Ozone, or O3, is the star of the show in this reaction. It acts like molecular scissors, snipping the alkene's double bond. This cleavage results in the formation of an ozonide, an unstable intermediate. But we don't want to stop at ozonides. To get our desired aldehydes, we need to break down these ozonides further. This is where a reducing agent like zinc or dimethyl sulfide comes into play. The reducing agent acts like a peacemaker. calming down the reactive ozonide and helping it transform into stable aldehydes. Section 6. Hydroformylation. Adding form to alkenes. Hydroformylation, also known as the OXO process, is an industrial workhorse for producing aldehydes. This method involves adding a formyl group, or CHO, to an alkene. In this reaction, we use a mixture of carbon monoxide and hydrogen gas along with a metal catalyst. The catalysts are usually cobalt or rhodium compounds which act like matchmakers, bringing the reactants together. The reaction occurs under high pressure and temperature, typically between 10 to 100 atmospheres and 40 to 200 degrees Celsius. These conditions might seem extreme, but they are necessary to encourage the alkene, carbon monoxide, and hydrogen gas to react. Hydroformylation is an efficient way to produce aldehydes on a large scale and is widely used in the chemical industry.